Until now, most of us have believed that the meteorite impact with Earth was the cause of the dinosaurs' extinction. But have you ever wondered if that's really true? A 6-mile-wide rock, falling at 20 times the speed of a bullet, unleashed power equivalent to 10 billion nuclear bombs. The meteorite was not what truly killed the Triceratops. At the end of the Cretaceous period, a type of disease, likened to a prehistoric biological weapon, ravaged countless species, and Triceratops was one of its victims. What I'm about to reveal will surely baffle your mind. And it could even change everything we thought we knew about the downfall of Triceratops. Among the most famous dinosaurs to have ever ruled the Earth, Triceratops has always been a special icon. With bodies ranging from 23 to 30 feet long and weighing 13,000 to 26,000 pounds, they were like living tanks of the late Cretaceous. The name Triceratops means three-horned face, a perfect description of this creature's appearance. 2 long, sharp horns above the eyes and a smaller one on the nose. Alongside that was a massive bony frill, like a shield rising behind the head, used both for protection and for display in fights or to attract mates. Triceratops were herbivores, using hundreds of teeth arranged in dental batteries to crush the tough foliage that grew thickly across ancient plains. When imagining a herd of Triceratops moving through the lowlands, dust swirling under their heavy steps, one easily thinks of an imposing convoy of war chariots, ready to face any predator bold enough to approach. That majestic appearance made Triceratops one of the most popular dinosaurs in both public fascination and scientific study, appearing in textbooks, documentaries, and famous Hollywood films. Triceratops was not a species that existed throughout the entire Mesozoic era, but only appeared in its final stage, around 68 to 66 million years ago, right before the fateful KPG extinction event. This was a time when Earth had experienced over 160 million years of dinosaur dominance, but nature was beginning to change drastically. Global climate tended to fluctuate unpredictably. In many places, dry seasons were harsh and prolonged, while in others, the environment was swampy and humid. North America, where Triceratops lived, was then a vast floodplain, cut by enormous rivers and swampy forests. This rich ecosystem nourished a wide array of large plants, from ferns and ancient conifers to rapidly evolving flowering plants. Triceratops became one of the dominant herbivores, thriving just before the giant meteor struck Earth and ushered in the age of mammals. This reality makes the story of the Triceratops extinction even more fascinating. They were among the last dinosaurs to appear, and almost instantly vanished as the Cretaceous period ended. Triceratops fossils are mostly found in North America, especially in the states of Montana, Wyoming, North and South Dakota, and some parts of Canada. The most famous geological layer filled with their fossils is the Hell Creek Formation, a giant dinosaur graveyard stretching hundreds of miles. Here, fossils of not only Triceratops have been found, but also T-Rex, Ankylosaurus, Pachycephalosaurus, and many species of duck-billed dinosaurs, hadrosaurs. This shows that Triceratops was a vital part of a complex ecosystem where giant herbivores coexisted with some of the most notorious predators. Scientists believe Triceratops adapted well to the flooded plains, where dense vegetation made it easy to find food, while their bulky bodies and sharp horns protected them from large predators. The distribution range of Triceratops was relatively narrow compared to other dinosaurs. They were almost exclusively found in northwestern America. This has led many researchers to believe that the evolution of Triceratops was region-specific, making them the final representative of the horned dinosaur group, Ceratopsidae, before the extinction disaster struck. In the ecosystem of the late Cretaceous, Triceratops played a role similar to that of modern elephants or cattle, massive herbivores that shaped the landscape. They could travel in herds of dozens, even hundreds of individuals, constantly moving across the plains in search of food. Each day, an adult could consume dozens of kilograms of leaves and soft stems, strong enough to snap even tough branches. With their massive build, Triceratops herds were not just grazing machines, but mobile barricades that forced predators to think twice. If T-Rex was the ultimate predator king, then Triceratops was the opposing stronghold. Many fossilized skulls show bite marks from T-Rex and even signs of bone healing, proving that Triceratops could survive attacks. This reveals that confrontations between the two species happened frequently, but predators didn't always win. This relationship created an ecological balance. T-Rex controlled Triceratops' numbers, while Triceratops provided a massive food source when they died or were taken down. One detail that makes Triceratops particularly intriguing to scientists is the pathological signs found on fossilized bones. Many of their skulls, horns, and frills show unusual holes, thickened bone edges, or deformities, all consistent with diagnoses like osteomyelitis or chronic infections. Some samples even show signs of bone tumors or corrosive ulcers, indicating the individual suffered illness for a long time before death. These injuries can't be fully explained by combat alone, because their distribution across many individuals in various regions suggests a more widespread cause, possibly bacteria, viruses, or parasitic fungi. This raises the hypothesis that Triceratops, like many other dinosaur species, may have faced disease outbreaks similar to modern pandemics. In the context of living in dense herds, a fast-spreading infectious disease would have been enough to devastate entire populations. From here, the theory of prehistoric biological warfare emerges, a scenario where Triceratops' enemies weren't just T-Rex or giant meteorites, but invisible microscopic organisms capable of altering evolutionary history. One of the strangest pieces of evidence about Triceratops is the presence of bone beds, sediment layers filled with fossils of many individuals of the same species, tightly packed in a small area. When paleontologists excavate rock layers at the Hell Creek or Lance Formation, they often encounter unbelievable scenes. Dozens, even hundreds of Triceratops bone fragments lie in the same layer, with the same geological age. This raises a big question. Why did so many giant individuals die almost at the same time, in the same place? If it were the result of a flash flood or landslide, we would see clearer geological chaos. If it were evidence of predation, the bones would likely show more bite marks and be scattered. Instead, these bone beds appear strangely calm, as if the entire herd collapsed within a short span of time, an image that immediately suggests a mass disease outbreak. In today's animal world, we've seen classic examples of disease sweeping through large herds. In Africa, anthrax can kill dozens of elephants in just a few weeks. In Asia, hemorrhagic septicemia can take the lives of hundreds of wild buffalo in just one dry season. When environmental conditions are harsh, prolonged droughts, scarce water sources, animals are forced to gather in the same area, creating ideal conditions for bacteria, viruses, or fungi to spread. If such a phenomenon occurred in Triceratops, it would provide a reasonable explanation for the bone beds. The entire herd may have contracted a deadly infectious disease, causing many individuals to die within days or weeks. As the corpses decomposed in the mud, floodwaters covered them in silt, forming the fossil layers we excavate today. In the modern natural world, one of the most terrifying examples of microbial power is the fungus Ophiocordyceps, also known as the zombie fungus. This fungus attacks insects, particularly ants, by invading their bodies and taking control of their nervous systems. Once infected, the ant no longer behaves on its own instincts but is instead compelled to climb to a high point and bite down onto a leaf or branch. The fungus then grows, emerging from the ant's head, and releases countless spores to infect others. This image evokes a chilling scenario. If a similar superfungus had existed during the Cretaceous, could it have turned Triceratops into mass victims? All it would take is one strain adapted to a massive body, and the fungus or bacteria could quickly spread through the herd, turning them into walking disease vectors. This idea may sound like science fiction, but in reality, parasitic fungi have existed for hundreds of millions of years and were fully capable of significantly impacting prehistoric animals. The climate of late Cretaceous North America was highly favorable to microbial development. Hot, humid, swampy forests and flooded plains. In such environments, molds and bacteria could easily thrive. Fossil evidence from some contemporary animals shows signs of disease, from bone tumors to infections. Modern research also proves that viruses can survive and evolve in such conditions, even if they don't leave direct fossil traces. If Triceratops lived in large herds, which many scientists believe, then a single infected individual would be enough to spread disease to the whole group through contact, shared food, or contaminated water. This hypothesis aligns with bone beds containing individuals of various ages, a common sign of epidemics, as infectious diseases often strike indiscriminately, regardless of strength or age. Another interesting angle is that predators may have played a role in spreading pathogens. Imagine T-Rex, the apex predator, attacking a diseased Triceratops. As it bit through the thick skin, blood and bodily fluids full of bacteria or viruses could cling to T-Rex's teeth and gums. The beast then goes on to attack other Triceratops, unknowingly becoming a massive disease vector. Just like lions today can transmit disease to antelope through bites, T-Rex may have acted like a giant syringe, injecting pathogens from one individual to another. Additionally, feeding on diseased carcasses could turn T-Rex into a bacterial reservoir, spreading illness into the environment. This opens up a chilling possibility. Not only did nature generate pathogens, but the behavior of apex predators helped sustain and spread them. As a result, Triceratops had little chance of escaping the invisible grip of disease. Picture a morning 66 million years ago on the vast plains of the Hell Creek Formation. A fully grown Triceratops, once the backbone of the herd, begins to show strange symptoms. It breathes heavily, its eyes are cloudy, and thick fluid drips from its nostrils. Within days, it grows weaker, stumbles as it walks, and occasionally stops to cough dryly. When it sneezes, millions of microscopic droplets spray into the air, settle on the low grass, and seep into the muddy grounds where the herd often gathers. Within a week, others begin showing the same symptoms, from small juveniles to massive individuals weighing tens of tons. The Triceratops herd, once a towering wall of defense against predators, now becomes a gathering of colossal bodies collapsing one by one. And while disease spreads silently, other shadows, T-Rex and Dakotaraptor, begin to notice the faint scent of rotting flesh in the wind. As muscle power is paralyzed by illness, Triceratops becomes easier prey than ever before. A species once considered an impenetrable fortress was now just a slow, helpless target. Just like that, T-Rex could easily take down a Triceratops without expending much effort. The idea that Triceratops could be wiped out by disease isn't just a far-fetched theory. The modern world has given us countless similar examples. In Africa, outbreaks of hemorrhagic septicemia have swept through herds of wild buffalo, killing hundreds in just a few weeks. In India, disease outbreaks among wild elephants have rapidly decimated populations, despite their massive size. In modern livestock farming, foot and mouth disease can spread at terrifying speeds, Just one infected individual puts hundreds of cows, pigs, or goats at risk of death. Animals that live in large, dense herds often share water sources, feeding grounds, and close contact, perfect bridges for disease transmission. If disease can wipe out a herd of buffalo in one rainy season, why couldn't it happen to Triceratops, which roamed in large groups across the Cretaceous plains? All modern biological rules suggest this scenario isn't just plausible, it likely happened. To better visualize this, let's try a hypothetical experiment. A herd of about 100 Triceratops is moving through a flooded area. Suppose one individual is infected with a respiratory disease that has a 3-day incubation period and a transmission rate of about 30% through close-range droplets. On the first day, the infected individual, patient 0, sneezes multiple times, releasing billions of tiny droplets carrying pathogens. Some land on grass, others remain airborne, and many fall into the shared waterhole the herd frequently drinks from. After 3 days, 6 more individuals begin to show symptoms. After a week, the number rises to 25. By day 15, over half the herd is infected. In a tightly packed group, the spread is nearly unavoidable. And if even one member becomes too weak, it becomes the first target for predators. Thus, disease doesn't just kill directly, it also opens the door for opportunistic hunters like T-Rex, turning the entire Triceratops herd into a giant banquet. Today, we know that many plants and animals use toxins, molds, or symbiotic bacteria to protect themselves or kill their enemies. Insects carry pathogens to mammals. Parasitic fungi turn insects into zombies to spread spores. In the grand picture of evolution, disease is a form of biological warfare that nature has employed for millions of years. For Triceratops, this scenario makes even more sense. Instead of imagining they fell only to the claws of T-Rex or a massive meteor, we can envision an invisible war playing out daily in their lungs, their blood, and on their skin. That war didn't produce spectacular bloody scenes, but it was quiet, relentless, and more effective than any other enemy. And perhaps, in the brutal survival game of the Cretaceous, it was those tiny organisms that were the ultimate weapon. The crucial twist in this scenario is, Triceratops may not have needed a meteor to go extinct. When the meteor struck Yucatan 66 million years ago, triggering the KPG mass extinction, Triceratops is often portrayed as an immediate victim of a cosmic catastrophe. But what if the truth is more complex? What if the Triceratops population had already been significantly weakened by disease? The bone beds containing many individuals that died at the same time could be evidence that their numbers had already sharply declined. When the meteor struck, it merely served as the final blow to a crumbling dynasty. Thus, the story of Triceratops extinction isn't just about the meteor, but a combination of multiple factors: erratic climate, environmental change, and above all, an invisible enemy called disease. In popular narratives, the meteor from 66 million years ago is portrayed as a sudden death sentence for the entire dinosaur kingdom. A giant fireball, hotter than the surface of the sun, crashed into Yucatan and wiped out all life. That image is dramatic, direct, and easy to understand. But when we closely examine fossil evidence, especially Triceratops, we realize the truth may be far more complicated. Instead of a sudden death, the extinction of the three-horned giant may have been a gradual process that began long before. The meteor wasn't the beginning but the end, the final nail in the coffin of a decline already underway. It's like an ancient tree that's been rotting from the inside for years. The final storm simply brought it down, but the true cause had eaten away at its roots. The story of death by disease wasn't unique to Triceratops. Human history too has walked the edge of extinction due to epidemics. Around 900,000 years ago, a genetic study shows that ancient humans went through a catastrophic bottleneck, with only about 1,000 individuals surviving. Medieval plagues wiped out tens of millions, erasing once thriving cities. The 20th century saw the Spanish flu pandemic, and the 21st reminded humanity through COVID-19 that even a tiny virus can paralyze the entire world. When we look at the pathological signs in Triceratops bones, we see a reflection of ourselves. Even massive, seemingly invincible creatures can fall to invisible enemies. Between humans and Triceratops, separated by tens of millions of years, there is one terrifying similarity: vulnerability to pandemics. If Triceratops didn't die solely because of the meteor, how many other species shared the same fate? Bone beds of hadrosaurs with dozens of individuals dead in the same sedimentary layer. Deformed ankylosaur bones suggesting signs of disease. Even in the oceans, many fish and marine reptile fossils show signs of mysterious mass deaths. We often assume that mass extinctions are caused by external events, meteorites, supervolcanoes, or global climate shifts. But how many quiet extinctions have occurred, leaving no ash clouds, no cataclysms, only holes and tumors etched into bones? Could it be that Earth's history has been rewritten many times, not just with fire and falling stone, but with silent epidemics sweeping through species, erasing them from the book of evolution? Triceratops was not alone in the ecosystem of the late Cretaceous. Alongside it was Ankylosaurus, the armored tank with thick plating and a giant tail club, and hadrosaurs, duck-billed dinosaurs that lived in herds and could emit far-reaching sounds like trumpets. If disease could sweep through a herd of Triceratops, then why couldn't it spread to other species living in the same region, sharing the same water and feeding grounds? Hadrosaur fossils have been found in large clusters, suggesting a form of mass death. Meanwhile, the heavy-bodied ankylosaurs, prone to joint and bone diseases, could easily have fallen victim to bacteria or parasites. By examining pathologies in the fossils of these species, paleontologists hope to paint a more complete picture. Not just Triceratops, but an entire ecosystem weakened by waves of disease before the meteor ever struck. If so, the cosmic impact was merely the finale to a symphony of extinction that had already begun. The story of Triceratops, when placed alongside human history, reveals a deeper truth. Dominance has never meant invincibility. Triceratops was once one of the mightiest herbivorous dinosaurs, with sharp horns, a massive frill, and a body weighing tens of tons. But all those weapons were useless against an enemy too small to be seen by the naked eye. Just like modern humans, despite our technology, medicine, and nuclear weapons, still tremble before a respiratory virus. That vulnerability isn't a personal weakness, but a law of nature. Every species, big or small, has a threshold against invisible pressures. Triceratops proved that even the grandest fortresses can collapse from within. And that lesson, across tens of millions of years, still holds value for humanity today. Perhaps the meteor ended the age of dinosaurs, but the story of Triceratops may have ended long before. The bone pathologies, the fossil beds filled with simultaneous deaths, all suggest the image of an invisible pandemic sweeping through the massive herds. That enemy had no claws, no roar, only tiny forms unseen by the eye, slipping into blood, into lungs, into every breath. Triceratops, the three-horned fortress of the Cretaceous, proved one thing: even the mightiest rulers can fall to invisible foes. Of course, this is just one of countless hypotheses regarding what truly pushed the dinosaurs to extinction. What I've presented is not the whole truth. I simply wanted to offer a more intriguing perspective on the prehistoric animal world. And after watching this video, do you find yourself wondering, could there be other species that were also victims of biological warfare, just like Triceratops?